13a that goes along with the writing in chapter 13. I want to show you something about triangles. Here we have created an equilateral triangle ABC, right? Now we've gone off each side of ABC and made an equilateral triangle off of the dimension of that side. Now, since these dimensions are all the same, we just end up with a larger, a two-frequency triangle out of the one frequency beginning triangle. Now, when we add on these triangles to these equilateral triangles to this side, and we find the center of them, right? Which is easy to do here and here and then through here and here. And you get the centers, you connect the centers, and you get another triangle. In this case, since we started with an equilateral triangle, we get this equilateral triangle perfectly centered, and there it is, absolutely similar. And this is an easy way to see that you can you're actually trisecting this line with these intersections. But you always get a new triangle when you connect the centers of a same dimension triangle put on the sides of any triangle. Also, you might notice while we're just looking at this one that this sets up a hexagon here by connecting the sides of both of these triangles. And if you if you look at it in a certain way, you can see that this is a diagram of an octahedron, a line diagram of an octahedron. I always find that interesting, that the Star of David is really is a line drawing of an octahedron. Okay, now we can take any triangle, which is what I really want to show you, regardless of dimensions, and make we take any triangle here, we add on our triangle based on this dimension, make an equilateral triangle on each side, find the centers of those triangles, connect them, and we always get an equilateral triangle. That is it shows how triangles try to resolve naturally and bring themselves into equilibrium. Okay. Now also we end up in this case with 1, 2, 3, 4, 5. We end up with a pentagon. So that's kind of interesting that it led us to that. Here's another one. It's just another triangle. We started with this triangle here and put triangles on each side equal to that dimension. The equilateral triangles equal to each side of the triangle. We connect the centers and we end up with an equilateral triangle again. Okay? Now, in this case of this first one, it suggests the hexagon right here. And so we're going to work with that hexagon. All right, look what we've got here. We have a hexagon, but now this triangle led us to the idea of a pentagon. Here's 5 sides. Okay, so if we take this hexagon and we bring it over like this, we end up with a pentagon, right? Now that's a stable pentagon by virtue of the table that we're setting it on, right? But here's the pentagon that self-generates out of 5 equilateral triangles. Okay, So this is in principle geometrically perfect, right? So you end up with a perfect pentagon, and then the distance across that those corners of the pentagon is phi, right? So so just looking at a triangle and seeing it self-resolve, we're already constructing the prime structures in the universe. So in order to stabilize the pentagon that we've created with the 5 equilateral triangles, we have to put another one on the other side, right? And then the connector in between is, these are all those dimensional constants, the prime dimensions, so that this center axis is this dimension, and phi is this expression here, 1 plus the square root of 5 over 2. Okay, and so that, I mean, we're back into our click stops, right? And it's self-generating right here before your eyes. Now, here's another picture of it, and here it is with the with phi indicated in there. And then there's two possible click stops. There's this one, and there's this acute one here, right here. Okay, now we take this same hexagon and we move it over 2 sides, right, like this, and we have our octahedron, right? Here we go. This is unstable too, until we put the other octahedron on the other side, and then it becomes a stable structure. And here that is, incorporating 1, 2, 3, 4. 4 triangles will stabilize and create the octahedron, which actually has 8. But you can build it with just 4. Okay, then we have, if we take that hexagon and we move it over 3, like this, we end up with our tetrahedron, right? Which is, here it is, and this is the click stop of unity right here. Okay, and then when we add another tetrahedron to this tetrahedron, we get the duotet, and we have completed our progression of the prime constants, and the all of the click stops are actually represented already in just what we did. Okay, that's how geometry or pure conceptuality and understanding these dimensions in this way, these geometries are actually speaking to us, right? I mean, and here's the icosahedron that is just the half of the pentagonal decagon, this thing right here, and then this is the phi, and this is the click stop that represents that. Okay, so that it's all so simple, right? And when you see the whole thing, it's really pretty exciting to look at it this way, Anyway, that's 13a. Now, in the next video, we're going to get into. We don't need any dimensions here. We don't need to measure anything or put any numbers on these diagrams or drawings. This is just generalized truth. Okay. All right.